In this video, we're going to discuss coordination geometry in the crystal field window. Let's talk about geometries first. So let's have a compound that's octahedral. We're going to have our transition metal in the middle, and we're going to have 6 different things around it. In this case, we're just going to use colored orbs. Let's have a variety. Let's say in this case, I have 4 of the white and 2 of the green. Well, there's 2 ways we can realistically attach these. The greens could be 90 degrees from each other. And that's true whether the 2 went down, the 2 were over here, the 2 were there. Any adjacent situation on this molecule, since effectively this looks like an XYZ axis, the axes are all 90 degrees off from each other, any adjacent is going to be 90 degrees away. This is called a cis configuration. However, it was also possible that as we associate these, I could have put the greens on opposite sides of the same axis. If that's the case, they end up being 180 degrees apart. Now, this is the only configuration you can do it. They could be on top and bottom, or they could be on the other axis, but they have to be on the same axis. When this occurs, this is trans. The same series of ligands on the same ion have the ability to coordinate and form a complex in multiple fashions. And these will actually have different properties. The difference between a cis and a trans arrangement for the same ligands can change colors, change reactivities, change stability. In fact, ligands on the same axis here actually interact with each other fairly heavily. And this can affect whether 2 ligands can actually be trans from each other. This type of difference for the same molecule, this is an isomer. This is a coordination isomer or a constitutional isomer. The idea is it's the exact same atoms, all bound together. The only difference is the positioning of them. There are, however, other types of isomerism. Some ligands have multiple atoms that are capable of adding, such as NO2. Often we think of the nitrogen, double bond oxygen, single bond oxygen, but it is also possible that you can have the oxygen bound instead of the nitrogen. In this case, we're talking about a linkage isomer. Which atom of the ligand is actually attached? As different atoms will have different electronegativities, how this affects the donation of electrons to the iron, and therefore how it affects the other electrons around it from the other ligands, will be altered depending on whether the oxygen or the nitrogen in this example is attached. And possibly one of the hardest ones to actually see at first is the chirality. Chirality is a reference to what's called a stereoisomer. Stereo from 2 points, like stereoscopic vision or sound. Stereoisomers are about the direction of attachment. What do we mean there? Well, let's imagine we have an octahedral complex again. We're going to put something green way down at the bottom, something white way up at the top, and around the middle, we're going to have 4 things. Well, let's imagine we look down from above. So our eyeball's here, we're looking down. What are we going to see? At first, very far away, there's a green object. Well, we're going to have our middle here be red. So on top of that, in fact, covering it would be the red. Coming off of that will be the 4 things, the 1, 2, the 3, and the 4. And above it will be the thing closest to our eyeball, the white sphere. In this case, our 1, 2, 3, 4, if we were to follow it around, is assembled in a way that appears to go clockwise. Well, we could still have the same relation. We could have green down. We could have our red central transition metal. We could have the 4 things coming off of it. But if we said it was 1, 2, 3, 4, and then closest to our eye was the big white one on top. What this looks like is a mirror image. If you imagine I had a mirror here, and I held this one up near it, Well, the atoms closest would appear closest on the mirror side. So the 4 would be right next to the 4. The 1 would be right next to the 1. Our other atoms would be a little further away. And then the 3 on top far away, the 2 on bottom far away. These are mirror images of each other. It still has our green on bottom, our red in the middle, the white on top. It has 1, 2, 3, 4 going around the center. The difference is it's counterclockwise this time. At first, this may not seem a big deal, but you cannot make these look the same. If I tried to rotate this, if I actually move the 1 over here to 2, and the 2 up to 3, and the 3 over to 4, and the 4 down to 1, if we try to physically move them, well, what we'll see is 1 gets here, 2 moves up, 4 goes down, 3 goes over. I have 1 in the same place now. And 3 even happens to be in the same place on both of these, but the 4 and the 2 are reversed. That's true if I keep rotating it. I can get 2 of the 4 central components to line up, but I can never get all 4 of them. If it was the same, we should eventually be able to rotate it to look identical. These are not the same. This is the idea of a stereoisomer. It's the difference in how you rotate things, in this case. Most common example for this is your hands. Imagine you got your hand and your thumb. Then you have your other hand with your thumb and index, middle, ring, and pinky. In this case, on our left hand, if we go from thumb to pinky, as we go across, you put your hands on the table in front of you and you look at your left hand, your thumb to your pinky goes counterclockwise. On our right hand, however, it goes clockwise. That spread of which direction you have to go to travel across your fingers from your thumb to your pinky is the opposite direction. For all intents and purposes, our hands look identical, except the direction they're assembled. But if you ever try to put a right-hand glove on your left hand, it doesn't fit. There is a difference between these. And this is pretty common with various complexes. It is possible with the right combinations of things that you can assemble in a way that spirals in opposite directions. Well, at first the reactivity ought to be the same. When this goes to interact with other things that have a direction, you can find conflicting interactions, such as a right-handed glove trying to go on your left hand. Your 2 gloves have their own chirality, your hands have their own chirality. When you try to then start mixing things that have different stereochemistry, different combinations come out. Some fit better than others, and so this can be a concern when various reactions are trying to take place, especially with biological molecules, which are prone to having a great deal of chirality, of having a lot of stereochemistry. And so here's a few ideas for the ways that our complexes can form. We can have cis and trans isomers for how they attach. We can have linkage isomers for which atom of a ligand attaches. And we can even have stereoisomers for which direction they were assembled in. Well, why do we care about how they're assembled so much? Well, it comes down to what happens with the ligands. When you overlap 2 orbitals, when you think about molecular orbitals, so here's a hydrogen's 1s, here's another hydrogen's 1s. When they overlapped, you had a sigma bonding orbital that should have put a lot of electron density in the middle, and you had a sigma antibonding orbital, which effectively destroyed all the density in the middle and spread it out on the outside edges. You ended up with molecular orbitals. 2 orbitals go in, 2 orbitals came out. Well, when I have an iron and it has a d orbital, and some ligand tries to interact with it, some oxygen with an orbital with electrons in it, when these bind, what we are doing is overlapping 2 orbitals and creating a molecular orbital for their interaction. Exactly what that molecular orbital is changes based on the type of ligand, how it connects, the strength of the connection. But the two you get out, the most bonding one is lower in energy and tends to look a lot like your ligand. The most anti-bonding one tends to look a lot more like your d orbital. And so to a simple approximation, we just kind of pretend that the orbital still is the d orbital. Yes, its size and shape will change slightly based on what's being bound to it, but that's beyond the scope of our class to calculate out the full molecular orbital for it. Roughly, it still generally looks like a d orbital. These are different enough in energy that the shapes don't alter immensely. How much they do alter, though, affects the exact amount of energy of that orbital. That is where the crystal field window comes in handy. Depending on the geometry, your orbitals will be overlapped more or less by the various ligands. In an octahedral system, the way the overlap ends up working is that it favors 2 of the orbitals going up in energy and 3 of them going down. So our original 5d orbitals split in order to accommodate the overlap with the ligands. Various other geometries will have slightly different splitting patterns depending on how well the ligands in that geometry overlap the 5d orbitals. Additionally, depending on how many electrons you have, can determine what your transition is. If we have a lot of electrons, and we're filling the top, then our transition is usually our highest energy electron going to another orbital. Such a situation is going to go to a much higher orbital, and so that's going to be a high energy transition, probably beyond the visible range. But if we have fewer electrons in our system, well, then it's possible for our electrons to jump up just within the d orbitals. This is a much lower energy transition and often can fall in the visible light range. This is part of why transition metal compounds are so colorful and vividly colorful. They tend to have very specific absorptions in the visible realm, giving us very specific missing wavelengths, and the resulting rest of the light takes on a very specific color. These can be complicated a little bit more by multiple transitions and give us a wide variety of colors that we see in various transition metal complexes. This has unfortunately led to a great deal of problems in the past, as various things like arsenic green was one of the early metal complex colors, and unfortunately would leach arsenic into the wearer. And slowly as they would sweat wearing fancy clothes, they would absorb that arsenic and die. More common things like Prussian blue, or midnight blue for crayon lovers, that's an iron cyanide compound. It's a complex of cyanides and iron, and that's actually remarkably stable. Those cyanides do not break off the iron very easily. As a result, that color was very stable, very safe to put on clothing, and was in fact one of the premier blue colors of the last century. Cadmium tends to make intense yellows, which unfortunately showed up in the paint on Tonka trucks for a while, which meant young children chewing on Tonka trucks would get a little bit of toxic cadmium. That's a heavy metal that never really leaves your system. It wasn't supposed to be there, but cheap manufacturers were using unsafe paint systems. So just a few examples there where transition metal complexes have shown up in our dyes and colorants and paints. How do we get these windows though? How does this affect, and how do we get still slightly different colors? If one set of transitions will give you green, how do you make it a slightly different green? For that, scroll back up. We look at our weak and strong field ligands. As our overlap occurs, we drive our more stable orbital down, and we drive our antibonding orbital up. The better the overlap, the stronger the interaction, the greater the difference in the energy. And so we can have, say, an octahedral window that has very small energy difference, or we can have an octahedral window that has a large energy difference, or any of the other possible geometries. How big that difference is when an electron gets excited determines what wavelength that light will absorb. And so if we can expand the difference just a little bit more, we can make it a little bit more energetic. We can force a little bit more energetic light to be absorbed. And that is what happens here. Certain ligands are stronger and able to create a greater difference in our crystal field window. These are called strong field ligands: carbon monoxide, cyanide, nitrite. Similarly, some of our ligands are particularly weak. They don't create a very big difference. Our iodides, our chlorides, our fluorides don't promote a very large difference in the energies of our d orbitals. As a result, they'll have a fairly small absorption. They'll absorb, say, in the red, leaving lots of blue behind. As we get to higher field windows, we'll be absorbing higher energy, we'll absorb lots of blue, leaving more red compounds behind. And so what ligand of this common set is used has a very pronounced effect on the color of the compound that comes out. And it's because of the slight differences in energy we see between the d orbitals as they get more and more spread out due to the overlap with the ligands. Well, if you ever take a 300 or a 400 level inorganic course, you'll dive much deeper into the geometries, the symmetries, the effects that has on absorptions, which absorptions can occur based on which geometries, how many different possible absorptions are allowed. Do we expect infrared absorptions? Do we expect ultraviolet absorptions? There are many, many, many deeper layers we can go with coordination chemistry. But as an intro to the concept of why our transition metals lead to so many beautifully colored compounds and why so many of them have been dangerously toxic over the era, this is the idea of what's going on with coordination chemistry. There's a lot of variables that can be adjusted, and as a result, there's a lot of different situations we can create, whether that's for dyes and things, or whether that's for catalysts, for reactions, or whether that's for modeling enzyme active sites in biosystems, or just oxygen transport in hemoglobin. Understanding that there's a lot of ways that transition metals can be bound by other things, and that they do this readily, is just the first step in the door to the complexities of transition metal chemistry.